Bismillahirrahmanirrahim. So last time we stopped at defining the matrix, and we said that the simplest way to define the matrix is just to count the number of hubs. So if I need to go to somewhere, I need to count the number of streets I have to pass through, regardless of how wide the street is, how crowded, what's the load, what is the length of that street. I don't count any of this. All I need to worry about is just the number of streets or the number of hubs I have to go through. But the matrix is more than that. So I can have multiple matrix. Okay. So I can have the bandwidth. So not just the number of streets I have to pass through, but the length or the width of that street, because the wider the street is, the more possibility I can go through that street faster. So, or in other words, the bandwidth is actually the width of the pipe. So if the width of the pipe is really wide, then this means that the packet will move through very fast. Or the delay, which is proportional to the bandwidth, basically. So the delay would be whether that delay is transmission delay or propagation delay or processing delay or something like that. So I can define the delay to be the metric, which means that if a link has low delay, this means that this link is better. Okay, or the cost or the metric would be in that case less. And then if I want to select the path from one source to one destination, so I select the path with the minimum summation of matrix across all the links. The load basically is that, the bandwidth is a theoretical bandwidth, right? The hub never changes, but the load changes in real time. The load itself can change in real time, and this is based on the fact that I go through this street and there is like a traffic jam, which is something real time. So the load in that case can change based on how much traffic is currently going over the link. Not just the bandwidth, because the bandwidth is just a theoretical bandwidth, how wide the pipe is, but the load gives me more real-time data. Or reliability, as we said, reliability talks about the probability of failure on this link. This link is reliable, and this link is not reliable. So the probability of failure on this link, if the probability of failure is less, this means that this link is better. Okay, and therefore the matrix will be low. So this matrix gets updated based on the protocol. As we said, if you're talking about distant vector routing protocols, then this matrix would be defined for the entire path. Like when you select on Google Maps, I want to go to this particular destination, it gives you one number, which is the time duration expected for you to get there. And in order to get there, you need to go into this direction. So it gives you the overall distance, but from this point, you have access only to the next hub or to the direction where you have to go through. But it doesn't give you, normally it doesn't give you the whole path. You need to go there unless you ask for it. So from one specific point or from one router, in our case, you have local information about which direction you have to take. And this direction should take you to the ultimate destination with a distance of that much. Okay? So this metric, whether this metric is the number of hubs or the bandwidth or whatever, so we calculate this metric for each individual link, and then if we have distant vector routing protocol, then these distances will get accumulated at this point. So at this point, I know that the distance between me and this destination, for example, is 400. This is the best distance. And in order to get there, I need to move in this direction. Okay? So in the routing table, this is how it looks like, the routing table. So for each network, we have the destination address. This is the destination address with the subnet mask to indicate the network address versus the host part. Where is the network part and where is the host part? Okay. And then here is where I have to see the metric. This is the metric. So we have number / number. The first number is what we call administrative distance, and this is what we will talk about later. Administrative distance, in brief, identifies the routing protocol that generated this route. Because in one router you can, in fact, run multiple routing protocols, RIP and OSPF and ERGRP all together. Okay? So which routing protocol generated this route? This is indicated by this number. Here, 120 indicates that RIP actually is the routing protocol that generated this route. Okay? There is another purpose of the administrative distance, which we will talk about later. So the second number here is the metric. The second number is the metric. So for example, 192.168.1.0. Which one is that? This one. This network. Okay? And this is the routing. This is R2 table. So R2 is this one. So this is the routing table of R2. This is R2. Okay? So from R2 to reach to network 192.168.1.0, which is the first entry, okay, it needs to go one hop, and the next hop is addressed 192.168.2.0, which is this in this direction. This is the network 2. Okay? So from router 2, in order to reach to this network, it needs to go one hop through this interface. That's what this route means. Okay? And this is the name of the interface, which means serial interface. We will talk about this terminology later. So the metric is in fact used differently by each routing protocol. For example, RIP uses simply hop count. Whether RIP version 1 or version 2, they both use hop count, which is the simplest. So I don't have to really know the bandwidth, whether this is like Ethernet or gigabit Ethernet, or this is wireless, this is what I don't have to do any of this. I only need to know how many links between me and a certain network or a certain destination. That's all. IGRP and EIGRP, they both use a combination of different values. The bandwidth and delay, and the bandwidth and delay are something that's offline values, which means that they depend only on the technology or the type of link, whether this is like fiber optic link or this is Ethernet link or whatever, okay? But they do not depend on real-time information, okay? The delay and the load and the reliability, they depend on real-time information, right? So they depend on the current situation on the link, whether there's traffic jams, whether there was like some failures in the past or no failures at all in the past. Based on that, I may actually update the load and the reliability in real time. The default ones are bandwidth and delay. These are used by default, as we will learn later. The load and reliability, these are not by default. You have to configure it manually to include the load and reliability. Regardless, I mean, the message here is that different routing protocols, they use different matrix. That's the message. The ISIS and OSPF, they use the bandwidth. They use only the bandwidth. Okay, so depending on the routing protocol, you know which matrix are used, and as we can see, you could actually use a combination of these values as a composite metric to indicate the performance on a link, or the cost that you need to pay on a specific link. Based on that, you accumulate this cost as you move forward. So at certain point, you have the total cost that you need to spend to reach to that destination, and what is the next hop. So that's what I need to know. If I need to reach to this network, I need to pay that cost, and I need to go through this next hop. Okay? But you do not know the whole topology. So router 2, as we can see here, router 2 does not have any global information about the topology. It only knows the cost, the accumulated cost to the final destination, and the next hop. Where should I go? Which in normal situation, what you get on Google Maps or any other navigator, that you need to spend this time duration if you go to this next hop. If you go to another next hop, maybe you will spend different duration, maybe longer, maybe shorter, and so on. Any questions?
What are you talking about? Which protocol? OSPF or in general, where you need to know the next hop and the cost bandwidth?
No, this is the routing table. This is an example of a routing table which is generated mostly using RIP. Okay? For OSPF and ISIS, as we said, these are link state protocols. For link state, you have what we call link state database. Link state database, you have the information about every single link. Every router has the information about every single link in the autonomous system or in the network. Okay? And then this link state protocols, usually they use this link state table in such a way to calculate which path I need to go through from beginning to end. Okay? Which one is the shortest path? We will talk about the details later. Okay? Okay, so I need to go from router 1, for example, to this network. Okay? So router 4 will give me the information that this network is directly connected. This information will propagate to router 3, from router 3 to router 2, router 1. Router 1 receives 2 metrics from router 3 and from router 2. Okay, and the 2 metrics happen to be equal. The 2 metrics happen to be equal. Of course, if we use the number of hops, in that case, they will not be equal. But assume we use different metrics, that router 1 receives from here and receives from here, and now they are equal. What do we do? Which one to take? Well, some routing protocols may actually select any one of them because the costs seem to be similar. So if I select this one or this one, it doesn't matter. Most of the routing protocols, what they do is that they actually they put in the routing table both routes. Both routes. Okay? So what does that mean? This means that we use a concept called load balancing. So instead of using this path only or this path only, what we will do is that we will divide the load. We can send one packet here and one packet here. Okay, so if the cost of 2 paths are similar or identical, then most of the routing protocols, they use the concept of load balancing. Load balancing means that we divide the load between the two paths. Okay? So we divide the traffic, the packets themselves. So the routing information gives me the information that those two paths are currently identical, and then the router will insert both routes in the routing table to indicate that you can do load balancing on these two routes.
So, like copying the packet?
Not copying, no. You send one packet here and one packet there. So instead of sending the whole traffic on one path, you send one packet here and one packet there. It's like you have a stream of cars going through, going from one point, and they can take two different branches. Okay? So instead of sending all of them in the same path, because the two paths are exactly similar, so you say, okay, this car goes here, this car goes there, this car goes here, this car goes there, and so on. This is what we call balancing the load. Because this will optimize the performance on the entire network. Because if we send all the packets in one path, okay, after some time, although this path is the best, but after some time, if we send all traffic to this path, this path will become the worst, because you're sending so the load on this path will become, it's like you're sending all the cars through North Road. So naturally, traffic jams will happen.
The same path means that the same distance, the same time.
Yes. Same path to the same destination. No, not the same path. Different paths to the same destination. Okay? So I want to get to TV roundabout. I can go through Khalifa Road or I can go through the North Road. Which one do I take? Well, if the two paths are exactly the same, then you send one car here, one car there. If you have this information, then you can balance the load on the network. Then everyone will be happy. Rather than just sending all cars through one route, then traffic jams will happen and so on. Okay?
And if they are different, not identical?
If they are different, then you don't use load balancing. You select the best one. By default, you select the best one. One exception to this, some routing protocols, they may actually select the best two routes. So they don't have to be exactly similar, but if the difference between them is really small. For us here, the rule is that if the cost is exactly the same, then we use load balancing. Okay? Otherwise, we select the best path. Okay? So, as we said, for the classification of the routing protocols, we talked about distant vector and link state. So this distant vector talk about vector of distances, and the vector of distances indicate the cost or the metric between the current point and the ultimate destination. And of course the direction. So they use the metric or the distance or the vector and the direction. But they don't. Each router does not have global information about the topology of the network. Examples of these protocols are REP, or Routing Information Protocol, Interior Gateway Routing Protocol, and Enhanced. So the Enhanced, as the name suggests, Enhanced is actually the evolution of the EIGRP. And both routing protocols are proposed or proprietary protocols that Cisco have actually developed in all their routers. So these two protocols are not, they call them like de facto standards. They are not international standards. But because the Cisco routers, they represent 99% or 98% of all the routers, so they are very common in such a way that they are becoming like de facto standards. Okay, but REP is in fact a standard. So there is RFC, or if you go to IETF website, you will see the RFC for REP. Okay. So we will study REP and we will study EIGRP. So again, the meaning of the distant vector is that the router uses this distance and the vector or direction. As we said, the distance represents the cost between my current point and the ultimate destination. Okay, the accumulated cost. I do not have any breakdown of this cost into multiple lengths. I only have the accumulated cost and the direction where I have to move from my point to the next hub. That's it. Okay? So that's the mean distance vector routing protocol. The general characteristics of the distant vector routing protocols, this is very important. Generally, there are some exceptions to this, which we will talk about. Generally, distant vector routing protocols, they use periodic updates, which means that the router, every, let's say, like 30 seconds, this is the exact number for RIP, for example. RIP uses 30-second interval. So every 30 seconds, it collects all the information in the routing table currently, and it puts them all in one update message and sends it as one hub broadcast. So one hub broadcast meaning what? It sends the same message on all interfaces. All the is like if we have a router like this, and the router has different interfaces. Let's say like this one is fiber optic, this one is coaxial, this one is Ethernet, whatever. So every 30 seconds, it sends one message, it generates one message, and then it sends this message on all interfaces as one hub broadcast. Okay, so that's the periodic update. And it uses the neighbors for the update, which means that each router will only know the information locally about its neighbors only. So a router 1 knows that it's connected, for example, this router knows that it's connected to router 4 and that it's connected to router 2 because these are neighbors. But it doesn't know that there is a router called router 3 exists on the network. It doesn't know that. Okay? Similarly, router 4 knows router 1 and router 3, but it doesn't have any information about router 2. Okay? Of course, when the update messages flow in the network, I will know the ultimate distance between R4 and R2, for example. I will get that accumulated distance because for each hub, I have to accumulate the cost of this link. So router 2, it knows that there is a destination network here, for example, and in order to reach there, I have to pay that cost. But it doesn't know that I have to go through R1 and then R2 and then the network. That information it doesn't know. Okay. So broadcast updates. So updates are sent as one hub broadcast. Is there any other alternative? Yes, we will talk about, again, some exceptions and some other alternatives to that. So I may, in fact, send the updates not using broadcast. I can send it using multicast or unicast. Okay? And every time I have to collect the entire routing table, which means that I don't send partial information. Every time I have to send the entire routing table, no matter how big this routing table is. And that's the periodic updates and those two features or characteristics, in fact, they represent some limitation on how big or how large the network is that uses this distant vector routing protocol. Usually, distant vector routing protocols are not that scalable for very, very large networks because of these two things, which we will talk about in a minute. Okay? So that's protocols. So distant vector routing protocols, they define like what we call the algorithm, and the algorithm performs these tasks. So it sends and receives the update. So the algorithm is the one that runs the timer, and after 30 seconds it says, okay, so now is the time for me to send a message, to send an update. Then it goes to the routing table, it collects all the information in the routing table, it generates the message, and it sends it across all the interfaces in one hub broadcast fashion. Also, the algorithm is the one that's responsible for, when it receives the update, it should process this update. Okay? So the way it processes it is that, okay, so now I know that I received an update from router 2. Router 2 is informing me that there is in fact a network which is directly connected to router 2, which means that the cost for router 2 to send to this network is zero, no hubs, 0 hubs, right? So when router 2 sends the information to router 1, it should increase the 0 to 1, which indicates that in order to send to this network, send through me, okay? And this means that the cost will be 1 hub. So automatically, what the RIP algorithm will do is that once it sends the update, it always increments the number of hubs by 1 in all the hubs, in all the destination networks, which indicates that if you want to send to this destination network, you send through me, and the cost will be incremented by 1, which means that you have to go through 1 extra hub. So, for example, if you have another network here from router 3, let's say, and this is connected to router 4, let's say, which has a destination network. So router 4 will send information about this network and will increment the number of hubs from 0 to 1. Right? So when router 3 sends information about this to router 2, the cost will be 2. When router 2 sends to router 1, the cost will become 3. So for every update, you have to increment the cost by at least 1. Okay? So in that case, router 1 will know that in order to send to this particular network address, the cost will be 3, and I have to send it through router 2. And so on. Okay? So the algorithm, what it does is that when it receives this route updates, then it has to check all the routes in this route update, okay, and compare it with the ones that are already existing in this routing table. Okay? Because if the network is large, it becomes a little bit tricky that you may go through different routes to the same destination. So which route should I select? Well, what it does is that it basically selects, processes the incoming update, and compare it with the existing ones. If the incoming route does not exist at all in this routing table, this means that there's no way of comparison. The only way for me to get to this destination is through the new route. So I will insert the new route in the routing table. But there may be some situation that I have an incoming route and I have an existing route to the same destination. In that case, I have to select which one is better, right? So if the incoming route is giving me a cost that's less than the existing, then I remove the existing and put the new one. But if the new one is giving me a cost which is much more, then I will ignore it and use the one that's existing. So that's how we generate this routing table. And this is done through the algorithm that we talk about. So first, we send updates, we send and receive update. Second, we calculate the best route based on these updates, based on processing these updates. And third, we detect and react to topology changes. If a network here goes down, if this network goes down, then the algorithm inside router 2 will be triggered right away. And it has to do something about it. Okay? What does it do exactly? It depends on which routing protocol we talk about. And we will talk about this in more details. So these are the three functions of any routing algorithm. It sends and receives update, and then it calculates the best path and install routes accordingly. And install routes does not necessarily mean that you always insert the route that's coming in the update message. Not necessarily, because the route that's coming in the update message may have very high cost compared to the one that's already existing. Okay? So if I know that I'm going from this point or from مثلا the university to Duhail roundabout or whatever in a cost that's let's say like 400. So the router, another router or another information came that in order to go to the Duhail roundabout, the cost will be 500. Do I take it or not? Of course not, because the one that's already existing is less cost, or it's shorter in that case. So I keep the one that I have and ignore the new one that's coming. And we'll talk about some exceptions to this. Sometimes I have to accept the one with higher cost, but based on certain conditions, which we will talk about. But in normal cases, I should always select the minimum cost, the path with the minimum cost. Okay, so that's the algorithm. What are the criteria based on which we say that this distant routing protocol, this distant vector routing protocol is good, or this one is bad? Or actually, this applies not only to distant vector routing protocols, but this applies to all routing protocols, really. Okay, so even link state. So how can we say that RIP is better than IGRP, or maybe eIGRP is better than RIP, or OSPF is better than eIGRP? Okay, so we have to compare the time to convergence. And we talked about the convergence. We said that the convergence is the state when all the routing tables inside all the routers become consistent, which means that any update that's coming to any router in the network will give no new information to any router in the network. Okay? So if a router receives an update, then it compares this update against the routing table. There may be a situation that the incoming update does not give you any new information, right? If that's the case for all routers in the network, then we say that the whole network reached convergence, which means that the network has become fully operable or fully functional, and we expect to have no routing loops, no flaws, no discrepancies whatsoever. They have reached, all the routers have reached to a steady state. Okay? So the criteria is not that we reach or not reach. The criteria here is how much time do we have to spend until we get to that state. Because if you are telling me that I have a network of, let's say, like 30 routers, and in order to reach conversions, you have to wait for about an hour. Technically, you are telling me that you have to work, I mean, this network will be partially functional, and you may have some issues, you may have some routing loops, you may have some packets routed by mistake for a duration of 1 full hour. That's significant. This means that I will never use this routing protocol. It's really bad. okay? But if I have to wait for 30 seconds, or maybe 1 minute or so, that's okay, okay? So that's why when they restart the network of the university, sometimes there is a startup time. If that startup time is 2-3 minutes, we can tolerate it. But if you're telling me you have to wait for 2 hours, then I mean I will not accept it. So this time to conversions is very essential. Also the scalability, as we just talked about, these are correlated in a way. Because sometimes scalability talks about the fact that the routing protocol will remain functional consistently by increasing the size of the network. So if you're telling me that the performance of the routing protocol will not be affected that much, okay, in the case when the network is small or when the network is very large, to me, this is very good, right? So by increasing the size of the network, the performance of the routing protocol does not get affected badly. So that's what we talk about. That's what scalability is all about. Scalability is affected a little bit by the route updates. So for example, RIP is not very scalable in nature. Why? Because if there is any network change and we have to wait for 30 seconds, well, if the network is small, chances are that change will propagate in the network very fast, right? But if the network is very, very, very large, then in order for two routers with like 30 hubs in between, in order for this router to get information about a network change on this router, it has to wait for 30 different updates, right? If each update is taking 30 seconds, you do the math. It's 30 seconds times 30 hubs. Okay? 900 seconds. 900 seconds is significant. It's like few minutes. I don't know how many minutes. I don't know. But it's significant, right? And it will get worse if the number of, when the size of the network becomes larger and larger. Okay? So if route updates are periodical and the duration is a little bit large, like 30 seconds, then scalability gets affected. Okay? Resource usage talks about the fact that this routing protocol uses so much resources in terms of memory, in terms of CPU time, which means that the algorithm is really complicated. Okay? And it requires so much memory. For example, if RIP uses the number of hubs as the metric, then the comparison will be very fast. But if the algorithm uses a combination of bandwidth, delay, load reliability, and so on, then the calculation of the cost on each link will take a little bit of time. The calculation of the entire cost to a certain destination takes a little bit of time, and so on. And the amount of memory required to store each of these values will be more. So, for example, IGRP or EIGRP uses more resources and uses more complicated algorithm, which requires more computational resources, more than RIP, for example. If we talk about link state routing protocols, even though the title does not include, but as we said, these characteristics apply, or these criteria apply for both, then the resources used become even worse. They consume more resources. Why? Because you have to store information about every single link in the entire network. Right? As we said, link state routing protocols, they have to store information, global information about the entire topology of the network. Then the resources required in that case becomes more. And then implementation and maintenance. Implementation and maintenance talk about the the simplicity of the implementation. Of course, RIP is much simpler. The algorithm is very simple. Okay? And maintainability or maintenance talks about the fact that if there is any problem in the router, it takes no time to really maintain it or change the values. For example, EIGRP uses, as we said, 4 different matrix or 4 different values for the composite metric, which is bandwidth, delay, reliability, and load. So you have to keep updating these values every now and then, especially if we're talking about changing these values every now and then in real time. So the load changes in real time. The reliability changes in real time. So you have to update these values every now and then. So this is what we mean by maintenance. So the implementation is more complex and it requires a little bit of maintenance, a little bit of update every now and then. So in that case, of course, REP will be much more attractive compared to more complicated routing protocol like EIGRP or something. So this criteria is what we normally use. To apply this criteria on distant vector protocols, distant vector routing protocols, again, in general, okay, we were not specifying any specific routing protocol. We're not talking about REP, for example. We're talking about the general category of distant vector routing protocols. Generally, for distant vector routing protocols, you have simple implementation and maintenance. So the level of knowledge required to deploy and maintain the network with distant vector routing protocol is not high. Why? Because you only need to worry about the local neighbors. You don't need to maintain and get information about every single link in the network. Okay? So in that case, the implementation of accumulated vector or accumulated cost is very easy, versus that you have to have a link state database of every single link in the entire network. That becomes a little bit of an issue. Again, low resources required, as we said, in terms of memory and computation. To calculate the accumulated cost, this is very easy task. As I said, like the number of hops, you increment the number of hops by 1. That's it. That's all you need to do. And then when you receive the update, you compare it with the existing one. If the cost is more, ignore it. If the cost is less, take it. Very easy task, right? Versus for link state, as we will talk about, OSPF is much more complex, because it generates all the link states in the database. It collects all information, and then when I tell it I want to go from this point to this point, then it has to go through all the different combinations, okay, to extract which one is the best for me. And it has to do that on demand, okay, which is a more complex task, of course. And also in terms of memory usage, to store all the link state in the network requires much more memory, okay, versus the distant vector routing protocol. Slow conversions, in terms of this, these are the advantages. So advantages, it's distant vector routing protocols in general are simpler to implement, and they require low resources. But on the downside, they require huge amount of time to converge, again, in general, because we will talk about exceptions to this. Slow conversions because of the fact that we use periodic updates. Okay? And because of this, they have limited scalability. Why? Because if there is any network change, you spend huge amount of time to propagate this change across the entire network, because the route updates are periodical. So I have to do it incrementally, and each one takes 30 seconds. So if the network is large, then the performance is affected. So I have to keep the size of the network limited. So the time to conversions is proportional to the network size. It's directly proportional to the network size. So if you have slow conversions, this limits the size of the network you have to deal with, naturally. And as we said, routing loops may happen. Why? If you use Google Maps, you are going, you're driving your car, and all of a sudden you head to a construction. Tough luck. So Google Map will tell you, move forward. There's no forward. So in that case, you have to take another route. You take another route, and you drive a little bit. Google Maps will tell you, U-turn. You go U-turn, and you hit the same construction. So what do? You do not have global information, right? Your brain does not have the entire map. So you don't know how to avoid this loop because you don't have global information. That's the exact same case of distant vector routing protocols. Because they do not have global information, they may in fact lead to routing loops. Okay? And there are ways to mitigate these routing loops, which we will talk about. So it's not like distant vector routing protocols are not functional. No, they are, but they have to use some methods and techniques to avoid. If these routing loops happen, they have to mitigate them somehow. Okay? Any questions? So let's dig into how the routing protocol actually works from the startup, from the moment that the network first starts up. Okay? So when the network starts up, usually every router will only know information about the networks that are directly connected to it. Okay? So through their interfaces, once you start the router, router 1 will know that there is a fast Ethernet network connected on this port. And it knows that there is a serial PPP link connecting it to router 2 on this port. Okay? So that's the only information it knows at the beginning. Similarly, R2 knows information about this serial link and this serial link only. R3 will get information about those two interfaces only. Okay? So that's why initially the routing table of R3 will have two networks, which is the 10400, which is this one, and 10300, which is this one here. Okay? And of course, the cost is 0 because they are directly connected. So as you can see, the common information here is that initially the cost is all 0 in all the routes because these are the directly connected routes. Okay? So this is the startup snapshot. This is the beginning of the network, which is what they call cold start. Cold start meaning network discovery. So each router will discover the networks that's directly connected to it only. Okay? If we do not start the routing protocol, because on the router, what you actually do is that you say start RIP, start OSPF. Okay? If you don't start the routing protocol, these routing tables will become like this forever. Will stay like this forever. Right? Because the only way for them to get updated is by exchanging route updates. And if you don't start the routing protocols, the updates will never get exchanged between the routers. Okay? So, at this point in time, we have to say start RIP, or start OSPF, or start EIGRP. Okay? Once you do that, then the update information will start flowing between the routers. So router 1 will send one update message that has those two networks with a cost of 1. We have to increment it by 1, and we'll send it through this interface and this interface. Of course, there is no router connected to this interface, then no one will pick it up, but on this interface, router 2 will pick it up. Okay? Similarly, router 2 will send information about this network and this network, okay, to both router 1 and router 3. Okay? Similarly, router 3 will send one update message with this network and this network, and will send it through to router 2. So let's take each update and see what it does exactly. So router 2 will send information about this network 10.2.0.0, and will send an update about this network 10.3.0.0, right? Router 1 will receive the message, will receive this update. The update will have what? Will have 10.2.0.0 with a cost of a 1. It's coming from router 2. This is an update. And router 2 has a cost of 0, so it should increment it to 1. And we'll have 10.3.0.0, and the cost is also a 1. So if you want to send, what does that mean? This means that if you want to send to 10.2.0.0, send through me and the cost will be 1. Even though this network is directly connected, but again, I don't know what's directly connected to R1. So I have to send information, I have to send the entire routing table to all interfaces, blindly. Okay? So router 1 will receive this update. We'll take the first entry, 10.2.0.0. Well, I have 10.2.0.0. What is the cost here? 0. And he's telling me the cost is 1. Which one do I take? 0, of course. I'm directly connected to. Why do I have to wait? Why do I have to go to someone when the network is directly connected to me? So it crosses this. I don't need it. Okay? And then it takes the next one, 10.3.0.0, and the cost is 1. Well, this one I don't have. Right? So in that case, I have to accept it. ماشي? So that's how it works, simply. So this one I will ignore, and this one I will take. Similarly here, router 2 will accept only information about this one from router 1, and from this one from router 3. And that's why it accepted 2 entries here. One for 10.4.0.0, which is this one, and 10.1.0.0, which is this one. And the cost for both is 1. Okay? Similarly, router 3 will accept only one route about this network. Okay? Which is the one that it doesn't have. So the question now is that, first of all, did we understand how we got there? Okay. So the second question is, have we reached convergence? So every time we have to ask ourselves, have we reached convergence? The answer is no. Why? Because this router, R1, still does not know anything about this network. This router, R3, still does not know any information about this network. Okay, so we have to wait a little bit before we decide on conversions. Okay. Next step. Now, R2 will send all the 4 entries now. And R1 will send these 3 entries, and R3 will send these 3 entries. Every time I have to send the entire routing table. Okay? It turns out that R3 does not have any new information to R2. R1 does not have any new information to R2, but the good news is R2 has new information to both. So when R2 sends the update, it should blindly increment the cost of this to 1, the cost of this to 1, the cost of this to 2, the cost of this to 2. Okay? Then, similar to what we have done before, R1 will get the information and then we'll compare it one by one. The cost of this is 1, 10.2.0.0. I have one cost with 0 cost. So forget about this. We'll compare each one until it finds out that network 10.4.0.0, I do not have any entry for this. And the cost is 2. So that's the best cost I have received so far. So it inserts this entity in the routing table. Similarly, router 3 will insert information about 10.1.0.0 with the cost of 2. Which makes sense because R3, in order to reach to 10.1.0.0, it has to go 2 routes or hubs. It has to go through 2 hubs. Okay? And for router 1 to get to network 10.4.0.0, again, it has to go through 2 hubs. Okay? So that's a state of convergence. If we try, if R2 now sends the update, R1 sends an update, R3 sends an update, you will never have any new information. Which means that these routing tables will remain like this until some topology change happens. Okay? It's not like they will stay like this forever. Of course, the network topology may change. Any question? Any question so far? So that's a state of convergence. So in that case, the router convergence is reached when all routing tables contain the exact same network information. And in that case, routers, for distant vector routing protocols, routing updates are periodical, right? So reaching the state of convergence does not mean that the route updates will stop. They will go periodic in periodical time forever. Okay? Because the route updates are not event-based. They are not triggered. These are periodical. So every 30 seconds, we will keep sending the entire routing table in the update message, regardless. Okay? Type. So, of course, in reality, the network is not operational correctly until it reaches that conversion state, right? Because before that, as we will see in a minute, there may be some missing information that may in fact cause some routing loops to happen, unfortunately. So before the network reaches conversions, the network is in a, we call it in a transient state. It's not fully operational. And if you send network traffic through the network before we attain the state of conversions, there is no guarantee that this traffic will in fact reach to the destinations correctly. So in a very large network like this, of course, in order for the information to flow all the way to the entire network, as we will see the number of hops here, the update messages have to go incrementally to all the routers in the network. And if one update takes 30 seconds, chances are this network will not be operable for quite some time. And that's why we say that distant vector routing protocols are, in general, not scalable, because they suffer from the slow conversions. Okay? So, the periodic updates is the main cause of this slow conversions. And periodic updates means that every time interval in RIP, the default time is 30 seconds. These periodic updates will get exchanged between the routers. Both RIP version 1 and RIP version 2, they both use the periodic updates every 30 seconds. So, for example, in the small network that we have talked about now, how much time do I need to reach conversions?
1 minute.
60 seconds, بالضبط, 1 minute. Because we had to wait for 2 different updates. Okay? The first time, all the routers, they send one update to each other. After 30 seconds, again, the same update happens. And in 2 updates, we have reached conversions. Every update takes 30 seconds, so the 2 updates take 60 seconds or 1 minute. So, and this is very small network, as you can see. So when the network becomes large, this will become minutes. Quite a few minutes, which in some cases are prohibitive. Does this mean that periodic updates is the only choice? The answer is no. Some routing protocols, they try to resolve this issue of periodic updates by implementing a different algorithm which has this set of characteristics. The updates are not periodic. They are not full updates. Okay? And they do not use broadcast. So EIGRP is the only exception in the distant vector routing protocols that does not use periodic updates. Instead, it uses what we call partial updates and triggered updates and bounded updates. What does each of these one means? Let's talk about triggered updates first. Triggered updates means that it's not periodic. When the network topology happens, then you send right away. You send the update right away. You don't have to wait for 30 seconds to expire until you send. So that's unlike RIP. So it sends triggered updates. When there is a network change, then you send the update. Okay? So this way, the conversions is attained faster. Why? Because once you send the update, it's triggered. You don't have to wait for 30 seconds. It goes to the next router. The next router will will consider it as a new update, so it sends it to the next router, and the next router will. So in a matter of few milliseconds, I can attain conversions. And then once you attain conversions, you stop the updates. You don't have to keep sending updates. Unlike RIP, which uses periodic updates all the time, even after conversions. So this one, it uses triggered updates. Once the conversions is attained, then you stop conversions. Then you stop sending updates and wait for any network topology change to happen. So that's what we call triggered updates. So triggered, يعني معناها ايه? Triggered by a network change or topology change. Okay? Type. So that's one. So we know that. So what partial means? Partial means that we do not have to every time send the whole routing table in the network update, in the message update. If I know that this network, for example, goes down, or maybe this network did not exist and now this network has come and it has been recently connected to the network. Why do I have to send the entire routing table in the update? So I only need to inform people, I only need to inform the neighbors about only the new route, right? Or the new network that recently connected to the network, right? So that's what we mean by partial. So I do not have to collect all the routing table every time. So first, it's triggered by the fact that this network is connected or disconnected or any topology change. So it's triggered, it's not periodic. Second, I only need to inform people about only the change, not about the entire routing table. Okay? So that's the second difference. The third difference is bounded. What does it mean? It means that I only need to inform the people that are affected by it. Only the ones that are affected by this change. Okay? So depending on the network topology, maybe this router will get affected. I will inform this router. But maybe here, for example, this network is not affected by the fact that there is a new route. So why do I have to send a message update on this interface as well? There's no router here. In RIP, I have to do it bluntly. Broadcast, I use the address, you know the broadcast address? All ones. Which means that the update will go to all the interfaces, regardless. Okay? EIGRP instead uses the concept of bounded updates. So partial updates, triggered updates, and bounded updates. Bounded means that I only need to inform the ones that are affected by the change. So I only generate the update based on event. I communicate only partial information about the new change, and I communicate it to people who are affected by it. These are the three main changes. But this is it's not easy. That's why RIP did not use that in the beginning, because in order to perform this, it's not an easy task. Okay? So the algorithm has to be much more complicated in that case. So if you want to be non-periodic, you have to do all of this. And it's not easy. Okay? Any questions? Okay, so we'll stop here.